Okay, so everyone, welcome back. So the next question that we have is basically we have there is example 25 as well, but I decided not to do that because I didn't understand the question. Okay, so I'm not doing example number 25. So example number 26. Example number 26 is consider f as a function from n to n, g as a function from n to n, and h as a function from n to r. From n to r. Defined as f of x is equal to 2x, and g of y is equal to 3y plus 4, and h of z is equal to sine z for every x, y, and z belonging to the set of natural numbers. Now you want to show that basically HOGOF is equal to HOGOF. Okay, so now the functions that we have here are basically these three functions. Now basically HOGOF as a solution, we can say that basically HOGOF is the same thing as H of GOF of x, right? So I can write this as H of basically GOF of x. So because I'm writing GOF of x because the input to the function f is x, so I'm writing H of GOF of x, right? Which is the same thing as H of GOF of x. I can write it as G of f of x. I can write this as G of f of x. And f of x is the same thing as 2x, right? Now I can write this as basically H of G of 2x. Now G of 2x would be basically 3 times 2x plus 4. So this would be H of 3 times, wherever you see in G, wherever you see the variable y, you have to put 2x. So that would be 3 times 2x plus 4, which is the same thing as basically H of basically 6x plus 4. Now H of 6x plus 4 is the same thing as basically H is sine z. So wherever you see the variable, you have to put 6x plus 4, which means that is equal to sine of 6x plus 4 for every x basically belonging to the set of natural numbers. So that is basically you can say that basically H of GOF g of f is equal to sine 6x plus 4, sine of 6x plus 4 for every x belonging to the set of natural numbers. So that's one thing that we can use later. And so that's one thing. Now we want to show that this HOGOF is equal to HOGOF. So now HOGOF, if I'm not mistaken, HOGOF is the same thing as H of G of Y is the same thing as so I can write this as so I can write this as basically HOG OF of basically, and the input over here would be X because the input to F is basically X. So what that means is that then basically what that means is that basically I have H of G of f of x, right? So I can write this as H of G of basically f of x of f of x and so what that means is that, so basically we need to pay attention to these steps. So HOGOF, I wrote it as basically, I wrote it as HOGOF of x. That you can do. There is no problem with that because the input to f is basically x, and so you can write it as HOGOF of x. Now, so then the next thing that we have here is that I need to write basically, well, I can of course write this as HOG of f of x. And bring this in and write this as HOG of f of x. Now f of x is equal to 2x. So I can write this as HOG of basically of 2x, and which means that this is the same thing as H of G of 2x basically, right? Which is the same thing as H of G of 2x, which means that wherever in G I see the variable, I have to replace that by 2x. So in G basically is 3y plus 4. G of y is equal to 3y plus 4. Now the variable is y, so wherever I see the variable, I replace it with 2x. So that's the same thing as H of basically G of 2x would be 3 times 2x plus 4. So 3 times 2x plus 4, right? And so this is equal to H of, that's 6x plus 4. 6x plus 4. And you know that H of x or H of z is equal to sine z. H of z is equal to sine z, which means that basically this is the same thing as sine of 6x plus 4 for all x belonging to the set of natural numbers, which means that basically which means that HOGOF, which you can write as HOGOF, is equal to sine 6x plus 4 for all x belonging to the set of natural numbers. And I can call this basically, I can call this 1, I can call this 2, and so 1 and 2 implies that basically you have sine of 6x plus 4, sine of 6x plus 4. So then you can say that basically HOGOF is equal to HOGOF. So this is basically this is a function, h is a function, and you are basically composing this h with the composition of two other functions, right? So h is over here, and you're composing that h with two other functions being composed at the same time. So then you can write this as the composition of the first two functions, and then compose the first two functions with the third function. So that is basically the what we learned from this exercise, or from this example, right? And basically the text says that this result is true. This result is true in general situations as well. In general situations as well, right? And then based on that, we will have a theorem, which is called theorem number 1. Theorem number 1. So theorem number 1 says that if f is a function, from x to y, if f is a function from x to y, and g is a function from y to z, and h is a function from z to s, if these are functions, then basically GOF is the same thing as HOGOF. That is basically the theorem that we have here, and we will prove this. But what you need to pay attention to here is that basically you see that the function f is from x to y, function g is from y to z, and function h is from z to s, meaning that basically the codomain of f is the domain of g, and the codomain of z, the codomain of g is the domain of h. If that is the case, then, and if these are basically functions, then you can write this relationship between the composite functions that you get from these three functions, f, g, and h. Basically HOGOF is equal to HOGOF, right? Now as a proof, you can say that basically we have HOGOF of x HOGO f of x is equal to h of GOF of x, GOF of x, so of x basically, so I can write it this way, GOF of x, and that is equal to h of g of f of x, for all x basically in the domain of the domain here, in the domain of f basically. So the domain is basically x here. Now HOGOF of x, HOGOF of x is equal to HOG of basically of f of x. So this is f of x, so I can write this as HOG of f of x, which is the same thing as h of g of basically h of, so I can write this as h of g of f of x, which is basically again the same thing here. So h of g of f of x for all x in basically in x. Hence you can say that HOGOF of x is equal to this thing over here, which is HOGOF, and that is basically the proof. Okay. Let's consider an example here. As an example, we have this is the kind of example that might confuse you, so we'll have to do it in different steps. 189. Okay. So example number 27. So you have, the question is consider f as a function from the set 1, 2, 3 to the set A, B, and C, and g as a function from the set A, B, C. So let me write this way, otherwise we will get, we might. So f is a function, and f is defined as f of 1 is equal to a. Let me write this as defined as f of 1 is equal to a, f of 2 is equal to b, and f of 3 is equal to c. Now we have another function g. Which goes from A, B, C. You can see that the codomain of f is the domain of g, meaning that A, B, and C goes to basically apple, ball, and cat. Apple, ball, and cat. And this is defined as G of A is equal to apple, G of A is equal to apple, G of B is equal to ball, G of B is equal to ball, and G of C is equal to cat. Right? So these are the two functions that we have. These are the two functions that we have. Now, we want to show that FG and GOF are invertible. We want to show that basically FG and GOF are invertible, and also find out F inverse, G inverse, and GOF inverse, and GOF inverse, and also show that basically GOF inverse is the same thing as F inverse G inverse. Right, so we want to do these three things here. Now, in order to do that, we need to go step by step, and we need to be a little bit patient in order to get to the end of this exercise. Although it's not that complicated or that lengthy. Okay, so now basically to solve this problem, we want to show that FG and GOF are invertible. And then of course we need to find F inverse as well. So as you can see, basically F is a function from 1, 2, 3 to ABC. F of 1 is equal to A, F of 2 is equal to B, and F of 3 is equal to C. That means that basically let me write this in some other color, for example, to show that F is invertible. To show that F is invertible, so then what you need to do is that basically F is basically a bijective function. F is a bijective function, meaning that it is both 1, 1. It is both 1, 1 and onto. Right? So every distinct element of the domain has a distinct element of the codomain as its image, and all the elements of the codomain are images of some element in the domain. A, B, C are all the three of them are images of some element in the domain. So that means that the function is both 1, 1 and onto, meaning that it's, well, what do you call it? Injective and surjective, we call it. So this is also called injective. This is also called injective, and onto is also called surjective. Right? So surjective and injective, which means that when both of them are the case, then we say that the function is bijective. And we said before that when a function is basically both injective and surjective, meaning that the function is bijective, then the function is then it's possible to find some for example F inverse in such a way that, for example, f inverse of a is equal to 1, and f inverse of b is equal to 2, and f inverse of c is equal to 3. So now let's define, you can define f inverse as basically a function from the codomain of f to the domain of f, from ABC to basically the domain of f, which is basically 1, 2, 3. And I'm going to define this function as basically f of a is equal to 1, f of a is equal to 1, f of b is equal to 2, f of b is equal to 2, and f of c is equal to 3. So what that means is that basically, as you can see, for example, the function f takes you from 1 to a, the function f inverse takes you from a to 1, meaning back from a to 1, The function f takes you from 2 to b, the function f inverse, and actually these are supposed to be f inverse. And the function f inverse takes you back from b to 2, and so on and so forth, right? So now in order to show that basically f is invertible, now we need to show that basically so now in order to show that f inverse is the inverse of f, we need to show that basically so we said that, for example, if you have two functions, if you have some function, for example, some function f from a to b, right? Suppose that you define some function in the same manner, but suppose that you call it, instead of f inverse, you call it g, and g goes from b back to a, right? Now I want to show that g is the inverse of f. We want to show that g is the inverse of f. Now in order to do that, we need to show that basically GOF is equal to I of A, the domain of f, the identity function on the set A, which is the domain of f, and also we need to show that FOG is equal to I of B, which is the codomain of f. If I can show these two things, then that means that if these two conditions are met, then what that means is that G is the inverse of f, right? And we have of course talked about this in terms of examples and in terms of theorems and proofs and everything, and so we know from there that this is true. So now I need to apply the same thing to this function, meaning that I have a function f, I have a function f inverse, and I want to show that f inverse is the inverse of f. So it's the same story here, except that here my notation is different. Here my notation is f and g. So how do I do that? So here I said that here we said that basically we need to show that G of is equal to I of A, meaning that basically G is the function which is supposed to be the inverse, and F is the original function, and A is basically the domain of the function F, right? So we need to show that basically F over here is 1, 2, 3. I'm sorry, the domain of F is equal to 1, 2, 3. We need to show that basically F inverse OF, meaning that the function that is supposed to be the inverse of F, composed with F, is supposed to be I of the set, which is the domain of F, which is basically this set over here, 1, 2, 3. I can write it as basically 1, 2, and 3 here as a subscript, or I can write it as F inverse OF is equal to I of, for example, I don't know, you can specify some letter here, for example, I don't know, if you don't have any A's over here, for example, you can write it as for example I of A, for example, where A is equal to, for example, 1, 2, and 3. That way I can write it as well, but we will leave it with this notation. This is understandable enough. So that's the first thing that I need to show. The second thing that I need to show is that we need to show that FOG, meaning that the function, the original function composed with the function which is supposed to be the inverse function, that is supposed to be I of B, meaning I of this the index, the identity function on this set. So that means that then I can write basically F inverse is supposed to be I of basically the codomain of F. So the codomain of F is basically this set over here, which is A, B, C. A, B, and C as a subscript. So now if I manage to show these two, then we can conclude that basically F inverse is the inverse of F. So now let's see how we can do that. So how can we show that F inverse OF is the same thing as I of 1, 2, 3? So F inverse OF is the same thing as basically is the same thing as F inverse of basically F of X, for example. F inverse of F of X. And let me write F over here so that we have something to compare to. So F basically is this function from 1, 2, and 3. Or let me actually make a screenshot. A screenshot would be much easier. So let me make a screenshot over here. Okay, so then we will take a look at the screenshot whenever we need to. Okay, so now basically, so now F inverse of F of X. Now basically F of let's since we don't have any rules for F of X, basically we have F of 1 is equal to A, F of 2 is equal to B, F of 3 is equal to C. We don't actually have a rule for this function. What I'm going to write is that instead of F of X, I'm going to write, for example, F inverse of, now what are the possible values for F? F is basically some function from from 1, 2, and 3, and it goes to some other set as, for example, A, B, and C, right? And we know that f of 1 is equal to A, and f of 2 is equal to B, and f of 3 is equal to C. That's what we know. So with that in mind, I can basically, the possible values that you can input into f are 1, 2, and 3. So let's see what happens if I input, for example, 1 into f. So I know that f of 1 is equal to A. So that is equal to f of A. I'm sorry, f inverse of A. F inverse of A. So we said that over here that f inverse of A is equal to 1. Right? So that means that f inverse of f of 1 is equal to 1. And also f, another possible value for f is 2 basically. So I can write f inverse of f of 2 is equal to, now f of 2 is equal to b. So that is f inverse of b. Now f inverse of b is equal to 2. So again, you can see that f inverse of f of 2 is equal to 2. And if I write f inverse of f of 3, for example, f of 3 is going to give me c. That means that this is f inverse of c. F inverse of c is equal to 3. That means that whatever input you give to, whatever input you have, that means that this function over here, f inverse of, is basically whatever input you give it from this set 1, 2, and 3, you will get the same thing back. Which means that basically this function, this composite function is actually the identity function on the same set. Because as we tried the value 1 as the input, we got the same thing back. We tried the value 2, we got the same thing back. We tried the value 3, we got the same thing back. And therefore we can say that f inverse of is the same thing as the identity function on the set 1, 2, and 3. So now basically there is one more thing that we need to show here, and that is f inverse is equal to I of basically ABC, right? So in order to show that, what I'm going to say is that basically f inverse is basically all of these values that you see here. So the different values that I can enter into f inverse are A, B, and C. So let's try, for example, A. Now f inverse of A is the same thing as basically f inverse of A, which is the same thing as, now f inverse of A is equal to 1. That means that f of 1 and f of 1 is equal to A. So as you can see, f inverse of A is equal to A. And again, you can see that f inverse of, for example, B here, f of B here is the same thing as f inverse of B, which is the same thing as f inverse of B is equal to 2, which means that this is equal to f of 2, and f of 2 is equal to B. And by the same logic, you can show that basically f inverse of C is equal to C, which means that, as you can see, f inverse, this composite function, all of these values A, B, and C, when I enter these values into the function, I'm getting the same things back, A, B, and C, which means that f inverse is actually the identity function on the same set ABC. So I can say that f inverse of basically is the same thing as the identity function on the set A, B, and C, right? So now we have shown that f inverse of is the identity function on set 1, 2, 3, which is the domain of f, and f inverse, this was f inverse of, and f of inverse is the identity function on the codomain of f, which implies that basically f inverse is the inverse of f, and f is invertible. F is invertible, right? So that was one part of this question. As you can see, this is a pretty kind of long question, but we need to go through each and every part of this question because there is things that we need to learn here in order to be applied to later problems. Okay, so now using the same logic that we used before, we can show that basically G is also invertible, because G, as you can see, G of A is equal to apple, G of B is equal to ball, and G of C is equal to cat, and so G is also 1, 1, and onto. So then you can argue that basically to show that G is invertible, you can say that basically it is obvious that G is a bijective function. Meaning that it is both injective and surjective. Since it is both injective and surjective, then you can call it bijective. Now, since it's a bijective function, you can define for example, some function G inverse, and normally the function that we had was basically G was a function from basically A, B, C to another set, basically apple, ball, and cat, right? So now G inverse, I define it as a function from this set back to this set, meaning that apple, ball, cat, and to this set A, B, and C. And then what I will do, I will write it such that G inverse of apple is equal to A, G inverse of ball is equal to B, G inverse of ball is equal to B, and G inverse of cat is equal to C. Now, in order to show that G inverse is the inverse of G, so to show that G inverse is the inverse of G, we need to show that basically Now the original function that I had was G. The domain of G is this set. The codomain of G is this set over here. So I have two functions over here. I have G inverse, which is supposed to be the inverse of G. And so I need to show that basically G inverse OG is equal to the identity set on the domain of G, which is basically A, B, and C. And I also need to show that basically GOG inverse is equal to I of basically this set, which is apple, ball, and cat. Apple, ball, and cat, right? So by the same logic, of course, you can show the same thing. You can show the same thing over here as well. Meaning that, for example, you can say that in order to show that, for example, G inverse OG is equal to I of ABC, let's find a couple of values for G inverse OG. So you can say that G inverse OG, and G, the argument to G is basically can be A, B, or C. Let's find the argument A, for example, here. That is the same thing as G inverse of G of A. Now G of A, as you know, is equal to G of A. We said that it's equal to apple, right? So G of A is equal to apple. So then you can see that G inverse of apple is equal to A, right? So that means that G inverse OG, when the argument is A, it's giving you an A. Again, you can say that G inverse OG of, let's say, another argument B, for example, is the same thing as G inverse of G of B, which is the same thing as G of B here is equal to ball, which is the same thing as G inverse of G of B is equal to ball. Now over here we said that G inverse of ball is equal to, for example, B is equal to B, and so on and so forth. And using the same logic, you can also show that G inverse OG of C is actually equal to C. Now you can see over here that this function G inverse OG takes A, B, and C as argument and gives you back A, B, C as arguments, which means that ABC, ABC, and that is the domain of G. That means that you can say that G inverse OG is the identity function on the set A, B, and C. On the set A, B, and C, which is, of course, incidentally, of course, the domain of G. And then using the same logic, you can show that GOG inverse is equal to I of this set over here, which is apple, ball, and cat, and which happens to be the codomain of G. And so based on that, you can conclude that basically G inverse is the inverse of G, and therefore G is invertible. G is invertible. Now, one more thing that we need to show here is that basically GOF is also invertible. Let me see if we have enough space here. It seems that we have. We want to show that we want to show that G of is invertible, right? So what that means is that basically, let's take a look at the functions that we have. We have the function f, which goes from this set 1, 2, and 3, and this goes to a set as basically a, b, and c, right? Now since you have that, and you know that basically f of 1 is equal to a, f of 2 is equal to b, and f of 3 is equal to c, meaning that f is bijective. F is bijective, meaning that it's both 1, 1 and onto. Also, we have another function here, which is g, which goes from what I'm thinking is that maybe I could put basically this general information related to each problem somewhere on this screen, and probably well, we could actually open 2 of these windows and then use one of them on the side, write the problem over here, and then solve the problem. We will try that in one of the next videos. Let's see how that goes. So here we said that basically f is bijective. Now g is another function that goes from ABC, and this goes to basically, for example, some other set, apple and ball and cat, right? And you know that g of a is equal to apple, g of b is equal to ball, and g of c is equal to cat. And so basically g is also bijective, meaning that it is also meaning that it is meaning that it is 1, 1 and onto, or you can say that it is injective and surjective, right? Now what we want to show is that if I call these sets, for example, if I give these sets a couple of names, for example, I can give these sets, for example, I can say that, for example, the set A is equal to, for example, 1, 2, and 3, and the set B, I'm going to call it as, for example, A, B, and C, and the set C, I'm going to call it as for example, apple, ball, and cat. And then based on that, we can then say that f goes from A to B, we can then say that f goes from A to B. And of course, you know that f is bijective, and then you can say that f basically g goes from B to C. You can say that g goes from B to C, and also g is also bijective. So what that means is that we have this simple situation that we have basically these 3 sets here, A, B, and C, and f goes from A to B. This is f. G goes from B to C, And GOF, which we are after here, is basically this function that goes from A to C. That is GOF. That is G of f of x. Meaning that if you have some x over here, you will get some f of x, and then if you give f of x as an argument to g, you will get g of f of x. Right? So what that means is that that is basically the situation that we have, and we want to show that GOF is invertible, right? So how do we do that? Okay, so now as you can see, GOF is a function that goes from A to C, meaning that I can write GOF is a function that goes from A to C, from basically from this set to this set, and that would be defined by, basically we said that f is defined as f of 1 is equal to a, f of 1 is equal to a, and f of 2 is equal to b, and f of 2 is equal to b, and f of 3 is equal to c. That is f from A to B. Now G from B to C is A to apple, B to ball, C to cat, right? So G of A is equal to apple, and G of B is equal to ball. G of B is equal to ball, and G of C is equal to cat, which means that GOF, which goes from A to C, maps 1 to apple, 2 to ball, 3 to cat. So you can say that GOF of 1 is equal to apple, and GOF of 2 is equal to ball, and also GOF of 3 is equal to cat, if I'm not mistaken. GOF of 3 is equal to cat. So now in order to get the inverse of GOF, we are going to define GOF inverse as basically GOF inverse, which is a function that goes from C to A, and that would be defined as basically GOF inverse of apple is equal to 1, GOF inverse of apple is equal to 1, and GOF inverse of ball is equal to 2, and GOF inverse of cat is equal to 3. Cat is equal to 3. Now in order to show that GOF inverse is the inverse of GOF, to show that GOF inverse is the inverse of GOF, we need to show that basically so the original function is GOF. The inverse function is basically GOF inverse, and so we take the second function, or the function which is supposed to be the inverse function, so g of inverse, and compose it with the original function g of, and that is supposed to be the identity function on the domain of g of, on the domain of f, which is I of a, and a is basically this set over here. And we also need to show that the inverse of this, meaning that that basically g of composed with basically g of inverse is equal to the identity function on the codomain of g of, which is c. That's basically what we need to show here. So now let's see how we can do that, but this video is getting a little bit long. So what I'm going to do is that I'm going to basically end this video here, and we will discuss this in the next video. See you in the next video, and thank you.